by now you understand CosmWasm state storage, at least the general principle of it, why it's needed, and how there are abstractions to make it easier to work with. The next abstraction, you've already looked at item, hopefully. The next abstraction is map. And map is similar to maps in a lot of other languages and frameworks. It is just basically multiple items that have some kind of index, a primary key that you can use to look up the items. And state storage is already a map. Everything you put into state storage has a key that finds it in state storage. But even in that, you can have a map within that map and have your own table structures, your own very flexible and very usable table structures right in state storage. This is actually where CosmWasm gets more powerful than a number of other platforms in regards with how easy it is to work with large amounts of values. So let's take a token info struct. Remember that we always need in CosmWasm storage, we're storing something that's typed. It can be any type that is serializable and deserializable, since it needs to be serialized to be stored in storage and deserialized from those bytes into your type. But it can be any type that fits those requirements. So we're going to create a map this time using the same constant terminology that we used with config in the items video. We map, and this time there are two items in here in this specifier, this type specifier here. With item, we just had item, and we had a type in there called config. And that just specified there was an item being stored, and it was config type. Here, we not only have to specify the type, we also have to specify what is the primary key type. So this is the key type, and this is the value type. We create that new map. Again, same terminology, same look as the item declaration in the last video, and we'll create it at the tokens location in the broader state storage. So there's this big key value map, and at that tokens location, we're storing a key value map of our own. And that is this tokens map. And it's going to be a bunch of strings associated with token info values. So token 1, info, token 2, info, token 3, info, and so on. We declare it like this. Of course, we use the token info type to create a new variable. In this case, we have Alice, and I needed something other than token name or ID, which presumably is the string here. So I just created a power item. It could be updated, whatever. This is an updatable value. That's fine. Power is 100 U64. And then we save to our map. Again, we need our storage, which for you is probably deps.storage or whatever you want to alias that to. And since we're saving, that's going to need to be a deps mute or a mutable reference, some kind of mutable storage. And then we not only have the item we're saving a reference to the value that we're saving, as with item, we also have whatever our new key is for the map. So you look at basically the three ways the location is being defined here. First, there's deps.storage, which is getting passed in. So we know it's in contract state storage. Then there's tokens, which is a map at this location in that storage. And then we set the key token 1. So within that location tokens, there's another map. And in that map, token 1 maps to this value. So we have our general contract store here, which is a hash map. And at the tokens location in that hash map, you see I have these dots on the left and the right. In theory, there's just infinite items on either side. But once you get to tokens in that hash map, right now there are no items on either side, but there could be all kinds of items. And at the tokens location in that map, we have our actual map, what we're calling our map here, tokens. That's the inner box. And then in that hash map at the token 1 location, and again, we could have any arbitrary number of items on either side. At the token 1 location, we have our actual token info there. So we look up in the storage, hey, I want tokens, and that finds our tokens map, tokens table, if you will. And then in that tokens table, we say, hey, I want token 1. and that finds our info. We load generally the same way as we did with the item, except of course we have to specify the key that we're loading at. So we can't just pass in our storage, which could be mutable or not mutable here for loading, but also passing in the key. In CosmWasm, it's convenient to use composite keys in some cases. We'll show an example on the next slide where I'm having this key type here. It can be a tuple. It can be a bunch of items chained together, which might be useful if you're looking up and you want to look up by the first or the first two prefixes in order to, or even the suffix, in order to filter down items and find items quickly. So here we have a string tuple or string slice tuple, and that is the key, and these are slammed together basically. So we have Alice and Bob. They together make up the key, the location, which, formerly was made up by Alice here. So we're saving Alice and Bob. So we can save Alice and Bob. Again, I'm not using the token info struct in this particular example, so ignore this temporarily. But in this case, I'm just saving a tuple as the key, Alice Bob, and then the actual value is this value here. Learn is brought to you completely free because of our great sponsors. Neutron, enabling developers to build breakthrough applications and onboard users from anywhere. Osmosis, the premier decentralized crypto exchange. And Obi, the smart new standard for asset management. If you want to become a smart contract developer through this lesson and others like it, head to heretolearn.xyz for uninterrupted course videos, coding exercises, and feedback directly from experts in the industry. So now at the key location Alice Bob, there's no more token 1 or anything. At the Alice Bob location, their team power is marked as 50. So the key itself is Alice Bob. It's not just Alice and then Bob is somewhere as a partner field or vice versa. It's not team 1 and then Alice and Bob are members. The key is literally Alice Bob smashed together. And that's useful because you might want to do something like this, where you have this team power table and you're saving Alice Bob, Alice Charlie, Bob Charlie, and these combinations of keys joined into actual keys, and then you call a prefix on it. You can call suffix as well. You call prefix Alice, and now you get all the Alices. So it's a simpler way to do multi-indexing things that we'll look at in more detail at index to map. But in some cases, this is a lot simpler than index to map to do composite keys. I could do prefix Alice, I can do suffix Charlie, I could do suffix Bob, and I'll end up with a vector of only the values that I'm looking for, rather than just the entire map. So it's a more primitive way to filter than indexed map, which is the subject of the next video, but it's a very useful way. We've used string slices here with Alice, but map can use arrays of bytes or vectors of bytes. It can use sized arrays of bytes, use string slices, actual strings, address, which is a CosmWasm struct that is often passed around since it implies that the address within has been validated, and any signed or unsigned integers up to 128. So you can have all kinds of keys. In fact, you can implement your own primary key and prefixing traits on a type in order to make it usable as a key. I wouldn't recommend you get into that right away, but you can do it in order to make arbitrary types, any types you want, basically, able to be keys for your map storage. You can also bound your requests. In other words, retrieve all requests after or before a certain point by key. And this is helpful for pagination, which I'll show directly on the next slide. Let's say I have a tokens map. Again, it's at the tokens location, and I have 2 tokens in it, token 1 and token 2, who are owned by Alice and Bob with these power items. So I can come in and create a bound, and I think you understand what an exclusive bound is. In this case, I'm creating a new bound that is either a start or endpoint, doesn't matter, but it excludes the item in parentheses. So token 1 won't be included. If I use it as a starting point, it'll be everything after token 1. If I use it as an endpoint, it'll be everything up to and not including token 1. There's also bound inclusive, inclusive raw, and exclusive raw. So if I put inclusive here, then token 1 would be included. Look at the next line to see what I mean here. I can take a range from my tokens map. It takes the store as its first argument, as we're used to with all of these things, the deps.storage. It doesn't have to be mutable here since I'm just reading. And I put a bound here, a start bound, and then an end bound, which can be none. So just keep going until the end of the map, right? The start is token 1, but it's exclusive. So this resulting item, I should have actually had let something equals tokens range. There's not much point to just calling tokens.range. In fact, this is a completely unfinished line, and I apologize for that. So let's say we let our results equal tokens.range, and we have a start bound that is exclusive token 1 and an end bound of none, then all the tokens after token 1 will be included, in this case, token 2. And so the second example here has a start and an end, and you see that this will include both because it's inclusive, token 1 and token 2. If there was a token 3, it would not be included at all because the start is token 1 and the end is token 2, and you've got a range. You can even order them, so you can even do it in reverse, which again, in a lot of contract platforms, it's hard to do this kind of stuff. We're not even index maps yet, but it's pretty easy to do it. You can do order descending, and you would be running this in the reverse order. Here I have a function that paginates for me. In other words, I have this list, this table, this map of token infos could be really long. I start at the beginning and then I have a limit, and the limit is a number. And I only take that limit from the range. So I will only take, say, 5 items at a time from my token info table. And then I have a start bound for future calls. So we can list tokens and say, give me 5, and then list tokens again and give the start point. And that is the last one we got, say token 4. Token 4 as the start after, and then a limit of 5 again, and we'll get the 5 items after token 4. And we could just continue safely, or getting a reasonable amount of values rather than some infinite number that may not fit in the bounds of a query, may not fit in our response, and we may not be able to retrieve that many. So we can retrieve pages of information from contract state, work with pages of information with this limit and this start after. So if I come in and say token 4 is my start after string, I say it's some token 4 string, then that is passed in here to a bound, an exclusive bound, because we already got token 4. We know what the previous or the last item we received was, an exclusive bound, and now all items after that item will be returned to us, or rather the limit of items, or 5 items in our example, after our token 4 will be returned to us. So this is the standard way to do pagination with a map. You have and it's standard to call it these things, start after and limit. And this way you can work with a lot of data without having enormous responses. You're going to have to work with a sizable amount of data in treasure chests. Continuing our treasure theme for storage, the map exercise is something you should do. And if you're not already there, at heretolearn.xyz/storage, where you can find interactive exercises, quizzes, and a whole CosmWasm learning book, as well as all the other great lessons in the CosmWasm Smart Contract course. This was a lot. If you should go do the map exercise. If you didn't watch items and you're confused by all this, items is simpler, and you might want to do the treasure trap exercise first. I'll see you shortly after for the indexed map storage video on your journey to being a CosmWasm smart contract engineer.